Hello everyone, this video is about variable acceleration and using differentiation to solve problems. Okay then, we go to here. So variable acceleration. Now, velocity. Velocity is a rate of change of displacement. And if displacement is varying and velocity is varying with time, then velocity as expressed as the rate of change of displacement is ds by dt. So if s is a function of time, then v is ds by dt. If we have a graph of displacement against time, then we draw the graph, then the velocity at any point is the gradient at that point. So velocity at any time is a gradient. Acceleration is the rate of change of velocity. So in a similar way, we express rate of change as dv by dt. Acceleration is the change of velocity, changes dv by dt, the derivative. So if you have a velocity time graph, then the velocity at any time is, or the acceleration, beg your pardon, at any time would be the gradient of the graph. So a is dv by dt, but v is ds by dt. So a would be the dv by dt of d by dt of v, which is d by dt of ds by dt. So that's a second derivative of s. So we can also express a as d2s by dt2. So this is how we would go from displacement to velocity to acceleration. We would differentiate. So you would go, if you start with displacement, to get to velocity you differentiate, and to get to from velocity to acceleration you differentiate again. Now that means because the reverse of differentiation is integration, if you wanted to go from acceleration to velocity, so supposing you had acceleration in terms of time, so you would go from acceleration to velocity, then you would integrate. And if you went from velocity back to displacement, you would need to integrate again. So this is how we would use differentiation and integration to go between displacement, velocity and acceleration, and back, acceleration, velocity and displacement. We'll cover the using integration in another video, but in this video we'll do some examples involving differentiation. So I'm going to go through this question, example 4, on page 185 of the Statistics and Mechanics book 1. Here it is. A particle P is moving on the x-axis. At time t seconds, the displacement x meters from O is given by x equals t to the power of 4 minus 32t plus 12. We sometimes use these variable x, we sometimes use the variable s for displacement. Either can be used. The time is always t though. And we want to find the velocity of p when t is 3, after 3 seconds, the value of t for which p is instantaneously at rest, and the acceleration of p when t is 1.5. Okay, so let's write down the function. We have x, the displacement, let's go to that colour. X. Ooh, we change there. Take it out again. Yeah, here we go. X equals t to the power of 4 minus 32t plus 12. So velocity is the rate of change of displacement. V then is dx by dt in this case. We're using x. And so we differentiate this expression. T to the power of 4 with respect to t would be 4t cubed. Minus 32t would be minus 32. When we differentiate 12, a constant, we get 0. So V is 4t cubed minus 32. So A, the velocity when t equals 3, t equals 3, gives V equals 4 times 20 t cubed. 3 cubed is 27. Oops. 27 minus 32. So that would be 108 minus 32, or 76 meters per second. So that's, well, the speed is 76 meters per second. Velocity is of course a vector, so we need to give a direction. Here the particle is moving along the x-axis, so it's one-dimensional, so we sort of have a one-dimensional. If we draw a line and make that the x-axis with O there, we have V is positive, so wherever the particle is, it could be anywhere. We make the particle there, then V is positive, it's going that way. But of course we don't know where the particle is. The particle could be over there. It doesn't matter. It will have a speed of 76 meters per second in the direction of positive x, so x increasing wherever it is. Part B says the value of t for which p is instantaneously at rest. As I said in the previous video, instantaneous rest means it's where the particle turns round. It's where the velocity goes, reduces to 0, and then keeps reducing, so it becomes negative, so it turns round. Or alternatively, it could change from going negative to positive. So the particle would be doing something like, it would be moving from wherever and go there, and then turn around and go back. It may well turn round again and go back like that. So it could do that sort of thing. These points, we would have V equals 0, the points where it turns round. So we want to find the value of t where V equals 0. V is 4t cubed minus 32. We put that equal to 0. Divide by 4. Put the 32 on the other side. Divide by 32. 4 will give you t cubed is 8. So we have t equals 2. So only one value, one time when the velocity is 0, only turns round once, in other words. So that's that. And then the acceleration when t is 1.5. So to find the acceleration, we would differentiate the velocity. So we had v equals 4t cubed minus 32. Be careful, I've seen people before write down t cubed minus 8 because they've put the 4t cubed minus 32 equals 0, divided by 4, and then had t cubed minus 8. Well, that's not what the velocity is. The velocity is 4t cubed minus 32. You don't divide by 4 here. You can factorise it, but you wouldn't divide by 4 unless you wanted to make it equal to 0. So acceleration is dv by dt, and so we differentiate 4t cubed. That will be 4 times 3t squared, or 12t squared, and 32 is a constant, so that goes to 0. And we want to know the acceleration when t is 1.5. Just looking at that. So if t is 1.5, we would substitute, and we have a equals 12 times 1.5 squared, which is, so that is 27 meters per second per second. Should have written seconds there. Okay. So it would be a good idea to have a little practice of that. A little practice of that, and go to page 185 to where you'd find exercise 11b here, and we have exercise 11b. You'll have some simple questions where you have to find the velocity and the acceleration, where you have the displacement. You can do a few of them and turn the page, and then you've got another, well, you've got another 5 on that page, where I think they're fairly simple, these questions involving differentiation. Probably 5 and 6 are the more interesting ones. Then you have a section on maxima and minima problems, just like this one here. I shall go through this example here in the next video. Alright, thank you.